All right, in this video, we're going to talk about timing diagram. So when you take the time delay into account into the timing analysis, so you need to draw a specific timing diagram in for a logic circuit. Okay. So for example, here is the example in the textbook. I think it's example 8.3. So the question is, draw the timing diagram and estimate the hazard. Right? So here's the circuit, the given circuit. 4 inputs and here I have an AND gate, here I have an inverter, and here has an inverter, and these 3 signals are being ANDed and then being ORed to the final signal. Okay, and there's a little description here. So initially A is 0 and B equals to C equals to D equals to 1, and C at one point C changes to 0 at time 2 nanoseconds. Okay, and draw the timing diagram. That's all the stuff, all the conditions being given to you. All right, now we know that here has a 2 nanosecond delay, here has a 1 nanosecond delay, 1 nanosecond delay, 2 nanosecond delay, and 2 nanosecond delay. Okay, that's everything given to you, and you need to find out the timing diagram and the static hazard, usually static 1 hazard, and fix it. Okay, this is everything given to you. So now we can start think about this. Because you have some intermediate signals in the middle, so let's just name it as, for example, this network calls F. So this is definitely C bar, and this is definitely A bar, and we call this F. So this is E, this is F. I'm sorry, probably I did say F here, but no, it's E here, F here. So we have names for every network node in the circuit. And now we can draw the timing diagram based on all these things. So before we do that, let's see, what is E? So E is BC, right? And what is F? F is C naught, A naught, D. What is G? G is BC or C naught, A naught, D. Okay, so you know what are these intermediate signals are. That's the final signal, intermediate signals. And you can definitely draw the timing diagram from here. So now let's take a look. So initially A is 0. 0 in the beginning. So of course A bar will be 1 in the beginning. Okay, and B, C, D will be 1s. So we have B is 1, C is 1, so C bar will be 0, and the reason we put C bar here is because we have a C bar participate in some of the operations here, so we need to draw the C bar here. And D is BCD is 1 in the beginning, so it's 1, and C changes to 0 at time. So for example, here And D, we also know E and F in the beginning, right? E, F, G in the beginning, I'm pretty sure. Because E is B and C, so B and C is actually 0. No, B and C is 1 in the beginning. And F is A bar, C bar, D. A bar, C bar, D. So that's definitely 0. And G is B, C, or A bar, C bar, D. So which is F, right? B, C, or F. B, C is 1. So it's actually E or F, right? So E or F. So definitely it's going to be 1 for G in the beginning. So for example, here's 2 nanoseconds. So at 2 nanoseconds, C changes to 0. And now let's see what's going to happen after that. So C changes to 0. So which means it's going to be 0 forever for the rest of the time. And there's one thing you will find out in the beginning. C has been toggled. So now let's see what the signals after C, what's going to be changed here. So definitely C bar after 1 nanosecond delay. C bar, for example, this is 1 nanosecond. C bar will be toggled. So this will be 3 nanoseconds, right? 2 nanoseconds after 1 nanosecond, you got 3 nanoseconds. And D, what is D? So D is still D. You know, D is not being affected. It's not an output of anything. It's going to be 1 all the time. So E, so we can see that E is BC, right? So E is B and C. But however, B and E is B and C, but has a 2 nanosecond delay. So B and C will be changed to 0, but 2 nanosecond delay, 1 nanosecond, 2 nanosecond, and it's going to become 0 for the rest of the time. So here will be, what is that? Definitely 4 nanosecond after 2 nanosecond delay. So what about F? F is A bar, C bar, D, A bar, C bar, D. A bar, because A is 0 all the time, so that's why A bar will be 1 all the time. So just ignore A bar here because it's a 1. So it's only look at C bar D. C bar D, D is 1. So it doesn't matter as well. So in the AND logic, you only take a look at C bar. However, for the AND logic, you are having a 2 nanosecond delay. So it's going to be changed. So F will be 0 in the beginning and will follow C bar and then follow that for 2 nanoseconds and being toggled to 1. 1 nanos will follow that, and after this, since C bar has been toggled, so need to wait for 2 nanoseconds here. So this will be 5 nanoseconds, and then you can see F will be toggled to 1. Okay, what about G? So G is E or F, right? But so the OR gate has a 2 nanosecond delay as well. So E or F, so in the beginning, E or F is 1, 1 here. So you're supposed to have a change, but you need a delay for 2 nanoseconds. So here will become 0, and then here should be 6 nanoseconds. So that's the entire timing diagram for this given logic. If they give you this kind of logic circuit and give you the time delay, you should be able to have the initial state and also the response from the output. Okay, and now let's find out the hazard. What's the hazard here? It's usually, when people are asking for the hazard, it's asking for the hazard as the output. So we are looking at G. Okay, that's a final logic expression. How can we find out the logic hazard from this? So definitely K-map, right? Yes, K-map. So we have AB, CD, 0001, 1110, 0001, 1110. And now let's see, what are they? If you have, you have to plug in all the numbers to find out what are these, what are G's, So BC, so for this one, so let's look at BC first. So whenever BC is 1, this entire thing will be 1 because it's our OR logic. So let's see which one have a BC to be 1. So B and C has to be 1 at the same time. So B here, right? C, so you have 4. BC, both BCs are 1s. And also for this one, you have to have A bar, C bar, D to be 1 at the same time. A bar, C bar, D. Oh, actually, they can be zeros, I think. Let me see. So when BCs are 1s, okay, yeah, so that's right. There's no problem with it. And then we need another thing which has to have A bar CD to be 1 at the same time. A bar, so it has to be here, these 2 rows, and CD, A bar CD. No, A bar C bar D. C bar D means C bar D. And so there are these 2 ones, these 2s. And we group them, and you find out the hazard. So here's a static 1 hazard, and you want to fix it by grouping these 2. So if you want to make that hazard free, you need to add this 2, which is A bar B D. So that one will make the entire thing static 1 hazard free. Okay, so that is how you design a if you see a digital circuit like that, actually you can find out the static 1 hazard by convert it into a K-map, and you find it out, you fix it, you redesign the circuit, you modify that. So keep in mind, if you can see a circuit, you can actually identify the hazard and fix it, and recover and add something to it, make a perfect circuit without any static 1 hazard. Okay, that's the way you do it, and I think this is everything we need to know for the timing diagram for the have with an example like this. And there's another example I want to show you for a pure timing diagram, just as example, so you are more confident when you are doing the exams and homework. Because the timing diagram is kind of like new to you guys, so I think one more example will make it perfect. Okay, so complete the timing for the given circuit assume that both gates have a propagation delay of, so propagation delay is just delay, right? Don't get confused here. So that's a really simple example. We have Wx as two inputs for this AND gate, and which has a 5 nanosecond delay, and then you have a Y as another signal and another 5 nanosecond delay. And finally, you get result Z here. Okay, and you have some initial signals being given here. So W was 0 in the beginning, and then have a little bump here, which is 10 nanoseconds, and X is something like that, and being toggled at this time point, and Y is this, and here has a bump of 10 nanoseconds as well. Okay, now you need to let us know what is Z look like. So that's the question here. Okay, so these are given. That's what you need to get. So we have an intermediate signal here. Let's just call it V. So what is V? V is Wx, right? So Wx that have a 5 nanosecond delay. Let's see. Wx in the beginning is 0 until here. Should become 1, but you have a 5 nanosecond delay. So no, not here. So until 5 nanosecond delay, you should have this 10 nanosecond. Wait, so how long is the end here? Yeah, 10 nanoseconds, right? Because they have a overlap area of 10 nanoseconds for 10 nanoseconds with both ones. So are going to get a 1 logic for 10 nanoseconds here, and then become 0 for the future. And now what about this? So it's a Y or V, which is Z. Y or V, so these two signals being ORed and with a 5 nanosecond delay. So it's going to look like 0 or 0 will be 0 in the beginning, and it will become 1, but however, with a 5 nanosecond delay, it's going to start from here. And so 1, 0 will be 1, 1, 1 will be 1, 1, 0 will be 1 as well. So it's going to last for a little bit longer after this. Will be 5 nanosecond longer, so it's totally 15 nanosecond here. Okay. All right, so that's how you do it. Just be careful about that. You need to get the intermediate signal, and then you just do analysis from top to bottom. Then you have to have this signal first, so it's available, and then you can find out the final result by using this intermediate signal with another input here. So it's pretty critical to get this first and do it in a specific order. Okay, so it's pretty straightforward. No too many tricky things, and that's a pretty simple example. And you'll probably see something pretty similar to this in the homework. Feel free to ask me questions if you couldn't get it. So for this one, thank you for watching. I will see you in the next video.